Detailed Standard Parasitic Format (DSPF) is a specialized, SPICE-compatible file used in integrated circuit design to represent parasitic elements extracted from the physical layout. These parasitic components are primarily resistance and capacitance that arise due to real-world interconnect effects and can significantly impact circuit performance. DSPF plays a critical role in enabling accurate timing, delay, and signal integrity analysis by modeling these effects in detail. The primary purposes of DSPF are: it facilitates the exchange of parasitic data between physical implementation tools and simulation environments, ensuring consistency across design stages. It supports circuit-level debugging by providing detailed connectivity and parasitic information, and it enables back annotation of parasitic data into schematics for verification and refinement. Unlike simplified formats, DSPF includes device connectivity information, but the main content is RC parasitics, making it ideal for full circuit-level analysis where precision is essential. While DSPF offers unmatched accuracy, it comes with the trade-off of larger file sizes due to its detailed representation. The example of the DSPF is shown here, which is used to describe parasitic elements and device connectivity for accurate circuit-level simulation. The header section begins with DSPF, indicating the file type, followed by metadata such as date, when the file was generated, and vendor, identifying the EDA tool vendor. The ADC sample hold line shows the design name for which parasitics were extracted. Next, we have formatting directives, divider and delimiter that define how hierarchical names and pin connections are separated, while bus delimiter specifies how bus signals are represented. The port order and case-sensitive yes flags indicate that port order and names are case-sensitive, ensuring consistency during simulation. Moving to the parasitic data section, lines starting with P describe parasitic elements for specific nets. For example, PNet1 pin 2 means that net 1 connects pin 1 and pin 2 with a resistance of 0.05 ohms and capacitance of 0.002 picofarads. Similarly, net 2 connects pin 3 and pin 4 with slightly higher parasitics. These values are critical for timing and signal integrity analysis because they represent real-world interconnect effects. The lines starting with I define instance connectivity for active devices. For example, the IX1M1 indicates that instance X1 corresponds to transistor M1 with its terminals mapped to drain, gate, and source nodes. This information enables the simulator to integrate parasitic data with device models for comprehensive post-layout SPICE simulation. This section presents a SPICE sub-circuit definition for the design ADC sample hold, encompassing both parasitic elements and active devices to facilitate accurate post-layout simulation. The line sub-circuit ADC sample hold VDD-VSS in-out defines the sub-circuit name and its external pins, VDD and VSS for power and ground, and in and out for signal connections. Inside the sub-circuit, the first section lists parasitic resistances extracted from the layout. For example, R1 net 1 net 2 0.05 means there is a resistor of 0.05 ohms between nodes net 1 and net 2, and R2 net 2 net 3 0.08 adds another resistor between net 2 and net 3. These resistances model the real-world interconnect effects that impact signal delay and power consumption. The next section specifies parasitic capacitances, such as C1 net 1 net 2 0.002 and C2 net 2 net 3 0.003, which represent coupling and loading effects between nodes. These capacitances are critical for timing and signal integrity analysis because they influence rise or fall times and noise behavior. Following this, the active device connections are defined. For instance, M1 with length L equals 0.18 micrometer and width W equals 1.0 micrometer describes an NMOS transistor with its drain connected to net 1, gate to net 2, and source and bulk tied to VSS. Similarly, M2 with L equals 0.18 micrometer and W equals 1.0 micrometer defines a PMOS transistor connected to nets 3 and 4 with its source and bulk tied to VDD. The parameters L equals 0.18 micrometer and W equals 1.0 micrometer specify the transistor dimensions, which affect its electrical characteristics. Finally, N's ADC sample hold marks the end of the subcircuit definition. In summary, this SPICE netlist combines parasitic elements and device models to provide a highly accurate representation of the circuit after layout. It is essential for post-layout simulations, timing closure, and signal integrity verification, ensuring that the design performs as expected under real-world conditions.